Welcome to a lesson on determining area using line integrals. If C is a simply connected piecewise smooth curve with a counterclockwise orientation in the plane region R, then the area of the region bounded by the curve is equal to 1/2 times the line integral of x dy minus y dx along curve C. And this is actually an application from Green's theorem. So let's take a look at where this formula comes from. We should now know Green's theorem stated here in red, and we should also remember from our studies of double integrals that the double integral over the region R integrated with respect to A would give us the area of region R. So what we're going to do here is look at a special case of Green's theorem when this difference here is equal to 1, and then we'll write this double integral here as a line integral in differential form. So if our vector field F has components little f and little g, then if we let f equal negative y over 2 and g equal x over 2, then the partial derivative of g with respect to x would be positive 1/2, and the partial derivative of f with respect to y would be negative 1/2, and that would give us the integrand of 1 because we'd have 1/2 minus negative 1/2. So if we use these functions and write the line integral in differential form, f dx would be negative 1/2 y dx, and g dy would be 1/2 x dy. So now if we factor out the 1/2 and then put the positive differential first, we'd have x dy minus y dx. And this is a line integral that will give us the area of the region as long as it satisfies the conditions of Green's theorem. Let's take a look at our example. We want to determine the area of the ellipse given below using a line integral. Notice how the orientation is counterclockwise, the curve is smooth, continuous, and connected, and the equation of our path is x squared divided by 16 plus y squared divided by 4 is equal to 1. So to set up this line integral, we'll parameterize our curve in terms of t, and then perform substitutions for x dy and y dx. So looking at our equation of the ellipse, if we let x equal 4 cosine t and y equal 2 sine t, we would satisfy the equation of the curve. So this also tells us that dx would be equal to negative 4 sine dt, and that dy would be equal to 2 cosine t dt. So we can use all of this to perform substitution into our line integral. So the area of this region would be equal to 1/2 times the line integral of x dy, that's going to give us 4 cosine t times dy, which is 2 cosine t dt. I'm going to go ahead and put the dt out here, minus y, which is 2 sine t, times dx, which is negative 4 sine t. And our limits of integration in terms of t would be from 0 all the way to 2 pi. Looks like we'll have 8 cosine squared t plus 8 sine squared t as our integrand. Let's go ahead and evaluate that. So if we factor out the 8, we're going to have cosine squared t plus sine squared t. That's equal to 1. So this simplifies nicely. This is going to be 8t times 1/2, that's 4t. So we're going to have 4 times 2 pi, that's 8 pi, minus 0. So the area of that ellipse would be 8 pi. Let's go back and take a look at that. Remember the geometric formula to determine the area of ellipse is a times b times pi. Well, a is equal to 4 and b is equal to 2, so that verifies our area should be 8 pi, which is what we found using a line integral. And that'll do it for this video. Thank you for watching.